Alright, so now for what appears to be a problem about belly buttons, but I think it's actually about math. So, anyways, we have A and G and we have IA, that we want to prove that IA is an automorphism. So, let's fix A and G. Then IA of 1 is A1 A inverse, which is A inverse equals 1. And for all x and y in G, IA of xy equals axia, which is, you can just throw an A inverse A in the middle there, and it becomes IAX. IY, so IA is a homomorphism. If IX, see here, if IAX is equal to IAY, this means precisely AXA inverse equals AYA inverse, and then just canceling yields that, so IA is injective. Also, for all x and g, IA of A inverse XA is AA inverse XAA inverse equals X. So IA is surjective and thus an automorphism. Okay, simple enough. Let's see here. As you can, I don't know if you've noticed this, but I like to give my maps names. It makes it a little easier for me to deal with them. I guess it kind of makes sense that they wouldn't do that in the problem statements, because I would just muddy up the notation. So I should write, now define phi legibly from G to aught G by phi of A is the map IA. And each of these IAs are automorphisms, so this indeed maps G into the automorphism group. What do we want to do? We want to prove that this is a homomorphism. So let's see here. Phi of 1 is I1, and this is clearly the identity map, because it's going to send any element to 1. It's going to send the element x to 1x1 inverse, which is just x, and so this is the identity. So let's see, I'm just going to call that 1, where 1 is understood as the 1 not in G but in aught G. And what else? We do the typical for all A, B, and G. And for all G and G as well, because we want to show because phi of AB is going to give us an automorphism, and so we want to be able to describe that automorphism, and the natural way to describe automorphisms is by evaluation at points, at least for me. So you take A, B, and G, these are going to be, so we're going to have phi of AB evaluated at G. So phi AB is an automorphism, and G, it's being evaluated at the element G. So this is just IAB of G, which by definition is AB of G, and then AB inverse. That's AB, GB inverse, A inverse. But look, this is A of IB of G, A inverse, and so it's just IA of IB of G, and that's just phi A times phi B of G, because multiplication in the automorphism group is given by composition. So, and this holds for all G and G, so phi of AB equals phi of A, phi of B. Thus, capital Phi is indeed a homomorphism. All right. Yeah, this is a long one, so we're going to do some scrolling, but we'll get through it. So now what we want to prove that the kernel is the center of G. All right. Now claim kernel of phi is the center of G, which I will denote by Z. You could also, this is a centralizer of G, right? Because it's the centralizer of G is the set of elements that commute with every element in G. Element of G. Whatever. I'm just gonna use Z of G because I learned this. Was this from Artin's book that uses Z of G to denote the center? Whatever. So here, suppose IA is in the kernel of phi. This means that for all x in G, IA of x equals AXA inverse equals x. And this last equality here, we multiply by A on the right, so AX equals XA. And thus, because this holds for all x in G, A is in Z of G. And so, let's see here. So then, let's see here, kernel of phi. Wait, this doesn't make sense. Kernel of phi is the center of G. No, the kernel of phi is IA, where A is in Z of G, right? We had a type error. Okay, so there we go. Kernel phi is contained in IA, where A is in ZG. Now suppose we start with some A in the center of G. Then we basically just go backwards for all x in G. AX equals XA. So x equals AXA inverse. We probably could have made an if and only if argument, but I don't know. Maybe not. This way is just as good. IA is in the kernel of phi, and hence that shows the reverse inclusion, and so we have kernel of phi is equal to IA, where A is in ZG. All right. So now define. I don't remember what we want to prove now. I'm just going to go by my notes and hope that we're proving what we want to prove. So NG is going to be the collection of IAs, where A is in G. Yep. Then NG is simply the image under phi of G. So by the fundamental theorem of group homomorphisms, in G is a subset of the automorphism group on G. And also we have in G is isomorphic to G mod ZG, because let's hear, why does all of this hold? This holds because capital Phi is a homomorphism, and in G is the image, and ZG is the kernel. Let's see here, is this the last page? No. So if we were to write this out, phi goes from G to G, then we have G mod CG. Oh, no. The kernel of phi is literally the center of G, because phi sends G to G. So let's fix that. So now suppose A is in G, and then which means IA is in the kernel of phi. But let's see here. So IA is the image of A. So no. So x equals 1AX. So phi of A is IA is 1, the identity element of G. So A as an element of G is in the kernel of phi. And so hence the kernel of phi is the center of G. Right? Yeah, I think this is what we want. So if we define inner of in G of IA, this is obviously the image of this. And so G mod ZG, that's a kernel, and this is a homomorphism. And so this is this map eta bar, as it's called in the textbook, is a isomorphism onto the image of capital Phi. And the image of capital Phi, of course, is in G, INN G. And so there we go. That proves that inner G is isomorphic to G mod ZG. And so we're done. Nope, just kidding. We got more to do. We got to prove that in G is a normal subgroup of G. Is there an easy way to do this using the fundamental theorems of homomorphisms? Maybe, but I'm going to do it directly. So to prove in G is a normal subgroup of G, let IA be an NG. Then, let's see here. Then for all x and g, we look at phi. Well, I might. So for all phi in the automorphism group of G, and for all okay, I'm gonna follow my script. So my script says I must prove that for all phi in at G and for all IA in G, phi inverse IA phi is also contained in inner G, i.e. phi inverse IA phi equals IB for some B and G. So let IA be in inner G, then for all x in G, phi inverse IA, remember we're going to do this pointwise, phi inverse IA phi of x equals phi inverse, and then IA of phi x is just A times phi x times A inverse. And what is this? This is the phi is automorphism, and so we can distribute it through. So we have phi inverse A, and then we have phi inverse of phi of x, which is just x, and then we have phi inverse of A inverse. And so this is just phi of A inverse x phi of A. And so this is I sub phi A inverse of x. And so the desired B in G here is the element phi A inverse. And so hence, so more precisely, phi inverse IA phi equals I sub phi A inverse, which is contained in inner G. Not C, but G. Hence, inner of G is indeed normal in automorphism of G as desired. And this completes our proof.